Welcome back, friends. So we have been discussing propagator methods in this set of lectures because we found that this is the right method to calculate things in a relativistic theory. Okay. So to begin with, we write the full Lagrangian in the relativistic format. We do not really consider potentials localized in the space time point but we consider as say for example we always consider the electromagnetic potential in the full in terms of the full electromagnetic equation, like in this fashion essentially. Say here I have given the example of the Dirac equation. We can do the same thing. We will consider several examples in the course of these lectures today and in the coming lectures. Okay. We will consider several examples of this type. We have already seen interactions with QED. So we will mostly focus on interactions which are electrodynamical interactions with scalars and fermions. We will also do one set of interactions between the scalars and the fermions. So that is called Yukawa interactions. We will do both of these things and then we will look at further at higher order corrections and stuff like that. Okay. So looking at this part, so the point is that you introduce interactions which are sort of given in this particular fashion in a Lorentz invariant way, where 1 by 4 f mu is nothing but your Maxwell's equations and the electromagnetic part, and the interaction when you write it in terms of the vector potential del mu f mu is equal to del nu a nu, the antisymmetric combination of del nu and a nu, okay, where a nu is the current or the vector particle or the current which couples to the J mu, the bilinear covariant of psi bar gamma mu psi essentially. So this gives you sort of the couplings between the fermions and the electromagnetic field essentially, which is nothing but a photon, which is quantized. We have not yet come to the quantization of a photon yet, but we will see essentially. For the present, let us just take it to be a wave, solution of a wave equation. So now, so what we have done is we just put it as a product of the wave functions of the fermions time which is a current, which is a gamma mu current, and in the Lorentz invariant fashion we coupled it with a photon current. So this is like a current interaction and this is Lorentz invariant, and so this fixes your interaction. On the left hand side you have them as free part Lagrangian, and the right hand side is also the free Lagrangian of the photon or of the electromagnetic wave equation essentially. So this is the thing. What the propagator theory tells you is that you can derive the propagator. So first of all, the propagator tells you that you have to do everything at action at a distance. So if you want to do interaction theory with this particular thing, whereas this particular the correct way of proceeding is to use Green's functions methods. So you want to use Green's functions method, but you use the Green's functions method in a particular fashion. So the particular fashion is as follows: we treat them as free particles, as coming in as free particles, interact with this photon current instantaneously at a particular point, space time point, and then get absorbed in the other vertex essentially, and then which goes out in the. So the instantaneous, that means these are treated as free particles. The way we are doing it is we are not trying to solve the equation exactly, okay, we are now trying to solve the wave functions in the presence of interactions. Instead of that we are treating them as perturbatively. This is important, and the way we treat them perturbatively is to treat the interactions as products of free particle wave functions. Interactions are free particle wave functions. So they act instantaneously at a particular point, at a particular space time point, and now this can be further applied for higher order in perturbation theories. Okay. And now how do you do the Green's functions then? If this is the case, how do you deal with these interactions? So suppose a simple scattering process, like two electrons come and go out, say for example they see each other and repel each other and go out. An electron comes, it radiates a photon, and this photon is absorbed by the other electron and they go out with different momenta. That is the basic idea essentially. So what is happening at, so the photon which is mediating between these two is called a propagator. It is called a propagator because at this particular point, I think I mentioned it several times, this for the electron current acts as a source for this photon field essentially. This electron current acts as a source for this photon field, but what we treat it as, because it is instantaneous at this particular space time point, that it is like a delta function. We do not solve it fully exactly, we treat it as a delta function potential source for this photon field. We treat it as a delta function source for this particular photon field, and that is what we call it as a Green's functions method essentially. So what we show is that just like solving the Poisson's equation. So when we solve the Poisson's equation in classical electrodynamics, where is the Poisson equation example? Okay, I think we solved it for the Schrodinger equation. So first for the non-relativistic example of a Schrodinger equation, we put a delta function and then we derived and put it, okay, non-relativistic propagator, we derived the propagator equation. So the propagator equation is nothing but this one, g of p is equal to, where is this g of p of the Schrodinger propagator? I am unable to control this one. Yes, this is the Schrodinger propagator. This is a Schrodinger propagator, and this is in the momentum space. It is given by 1 minus omega minus p square by 2m plus I epsilon. I will tell you about the I epsilon prescription in 1 or 2 lectures, essentially within the 1 or 2 lectures. And then we looked at the case of the electrodynamics and derived the case for the electrodynamics propagator to be this. And then we derived for the Klein-Gordon propagator. So what are the steps involved in deriving the propagator solution? The propagator wave function is that it is not going up. The propagator wave function is that the solution, the steps involved are write the equations of motion with the delta function source. So this can be true for anything essentially. The photon field acts as a source for the electron field essentially, and the electron current acts as a source for the photon field. So in general, because we are not saying specifying the interactions, essentially the propagators are sort of independent of the kind of interaction you have, the strength of the interaction and everything, okay, because we are always dealing with perturbation theory essentially. So write the equation of motion with delta function source, express the LHS in the wave function in Fourier modes essentially. So the equation of motion of the wave function, so when you write the wave function can be written in terms of Fourier modes or in the momentum space, and express the delta function on the right hand side in terms of Fourier modes. Again you can write it in terms of e power ikx and x minus x0 or whatever it is essentially. Then put these two expansions back into the equation of motion, and then you can extract the propagator in the momentum space. Typically propagators are done written in terms of momentum space because you do all the calculations in momentum space, okay. All the scattering problem and everything calculations are typically done in momentum space. Of course you can do in the position space also, but it is non-intuitive. And then we also discussed the case of some important properties of the propagator theory. One is that it only depends upon x minus the distance between the 2 points x minus x0, as long that means it is always translationally, as long as the theory is translationally invariant. Sum of all the solutions of the differential operator is the propagator essentially. The propagator is nothing but the sum of all the solutions. This we have seen explicitly, for example in del square is a propagator, and phi n and phi m or all the solutions, the sum of all this outer product is nothing but your g of x and x. And the most important point is that in the relativistic field theory, the propagator is not the solution of E square is equal to P square plus well m square, because you put in a delta function source. So, the propagator is not a solution, which are not. So, it is not exactly equivalent to E square plus P square plus m square. So, these are so the propagator contains virtual particles also, which do not satisfy energy momentum dispersion relation. So, these are short lived particles allowed by the uncertainty principle. They live for a short time and they have energy and momentum which is different as given, which is different from E square is equal to P, which does not satisfy E square is equal to P square plus m square. That means they are something called off shell solutions. And there could be on shell also, in which on shell means E square is equal to P square plus m square, and off shell means E square is equal to P square not equal to P square plus m square. So, this is another word for virtual particles. These are particles which are not detected in any experiments, but they can be in the propagator. The propagator contains real and virtual particles, where if it is a real particle it lies on shell, and but the solution of the propagator is not just that, it also has virtual a lot of bunch of virtual particles essentially. Okay. And physical particles will only detect on shell particles, that means they won't detect off shell particles. So, the scattering has a virtual particle being emitted by one of these currents to the other side, essentially to the other side. Now, then there is this important thing that physical experiment, the propagator we call it again in the absence of interaction. So, this is not a complete propagator, because the exact propagator would require corrections to the in the presence of interactions, because the solution we are considering for the propagator equation is the free particle equation of motion, and the source is just the delta function source. It is just the free particle equation of motion, but if you want to include interactions, then the exact propagator has to be calculated, which is very difficult to calculate. So, what we will do is we will only do corrections to the exact tree level propagator or the basic free particle propagator, which is also called the tree level propagator, and then keep adding corrections through it perturbatively. We will see that in a second. And finally, we also discussed the Feynman-Stackelberg interpretation of antiparticles. So, if you start drawing Feynman particle paths in terms of flow of charge, say for example either in this thing, in XNT, in space time diagram, in XNT diagram, when you have a particle antiparticle pair creation, what happens is that you have a flow of charge which is opposite in the direction of time. It is like, because it moves into the negative side of the direction, essentially, because you should remember that the antiparticles have exact opposite charge of the particles. So, that means they will pick up, their flow of the charge would be in opposite direction, and that if you represent it in space time diagram, it would look like particles are travelling backwards in time. If you want to interpret it physically, you interpret it as particles travelling backward in time. So, here there is a pair production, essentially you have one particle going in opposite in direction, one particle going in forward direction. That means at this particular point you are having both particles which are it is like a pair production. It is a particle going opposite in time and a particle which has a negative charge. So, which has a opposite charge. So, the charge lines would be completely different, essentially. You see this particular point, and in the circle you have both the charges are in opposite direction. So, Feynman and Stackelberg said that antiparticles are nothing but particles travelling backward in time, Okay, you have to treat them as particles travelling backward in time and with a positive energy, with a positive energy. So if you take it with a negative time, then energy becomes positive, okay, because finally what comes in all this equations is Et, okay, what you get is essentially Et. So particle creation and annihilation is P mu, and antiparticle creation and annihilation is minus P mu, because it has negative energy essentially. But instead of negative energy, if you take negative time, that means travelling backwards in time, you get positive energy. That is the basic idea, that antiparticles are travelling nothing but particles travelling backward in time with charges reversed essentially. So that means that because the charges are reversed. So this is where we have seen till in the last lecture. Now with this background, we come back again to calculate simple scattering process essentially given by a given Lagrangian. Okay, we will start thinking of simple process and compute try to find the solution of the wave function using the Green's functions methods, and that will automatically give you rise to these diagrams which are okay, which are corrected by corrected by the interactions. Okay, so let us go back to simple process. I introduced the notation of scalar QED some time ago. As always, we will start with scalar equations, and then we will move to the fermionic part. I will do this, and then I will do the fermionic propagator, and then I will do simple process and QED. Okay, the scalar QED Lagrangian SQED Lagrangian, which I have written long time back, essentially is nothing but del mu phi dagger del mu phi square phi dagger phi by 4. So let me expand this one. So this is the interactions, the kinetic term contains the interactions. I wrote it already in terms of a covariant derivative because it makes our life easier, and then this is just the mass term, and this is just the free part essentially. So let me divide it into free part and the interaction part. Now this gives me the free part as so on so term. There is an additional term which is product of these two. Let me write that part also, we will come back to it later on. Now look at this particular thing, this is the interaction term we have, this is a mu phi del mu phi dagger. Now del mu phi dagger phi del mu, this is the thing but the current which we have seen, which is the charge current which we have seen earlier essentially. So the photon couples to, or the photon or A mu couples to phi dagger del mu phi. So, we have this as the interaction, this is the current J mu of the photon field J mu phi, and this is the photon current. Let me tell you that it is the wave function of the photon wave function. We have not the electromagnetic wave function essentially. So, with this thing, okay, we are already in a position to do some simple process under how a phi interacts with another phi. Okay, a phi interacts with another phi, say for example phi to phi scattering. Let me just say that, let me have a photon, a particle phi which is a pion, let us call it a pion, phi is equal to pion. Okay, pion is a particle which has a positive charge, and phi dagger is pi minus, which is anti-pion. So, what we are looking at is pion in electrodynamics, pion electrodynamics. It is also called scalar electrodynamics. Now, what I want to say is that this entire thing can be calculated without actually doing full, without actually knowing full quantum field theory. Okay, we will need the full quantum field theory justifications, but by simple rules we can actually, with the Green's functions methods, we can do it. Scalar electrodynamics or pion electrodynamics. And you can use something called the Dyson equations to show that all these rules will come up in terms of this interaction picture essentially. Now, the first step is that I want to consider a scattering which is phi plus pi minus pi plus pi minus going into pi plus pi minus state. This is a simple process, two pions are coming in and going out of opposite charge. So, this is the process I want to calculate. This is the simplest process, two pions, these are charged particles, okay, which are oppositely charged. We will come to like charges also in a second. Let us consider pi plus pi minus going into pi plus pi minus. This is the simplest process one can think of. Okay, this is the simplest at leading order. We want to calculate in the coupling constant, at leading order in coupling constant. So, what we do, we have the Lagrangian in front of us, and the interaction part of the Lagrangian is this. The interaction part of the Lagrangian is this entire business essentially. Okay, this entire business is your interaction part of the Lagrangian. This is all the interaction part. Now, you can neglect this because it comes at with E square, at leading order it does not contribute. So, for the first step I will not consider this. So, I only have this particular thing. So, I want to solve it in terms of a momentum. Now, let me just see this interaction. What is the interaction telling you is that, let me go to greater detail into this particular interaction of the Lagrangian. What is that it telling you? Telling you that if you have a pion wave function, so the interaction is a interaction part of the Lagrangian is a why it is not changing the color, a mu phi dagger del mu phi. Okay. So there is this current for which is the scalar current and which is multiplying the for electromagnetic current okay, in this particular fashion. Now the point is that this current, the what are the appearing things, we do not know how to calculate these wave functions essentially in the presence of interactions. So what we do is we take them as free particle wave functions. So free particle wave functions of the scalar field are nothing but your plane waves. Okay, these are nothing but your plane waves. Okay, so this is like a plane wave coming in at the vertex because it is all at a vertex, and a plane wave going out. So this is with a charge. So if it is a positive charge comes out, and this particle also has a momentum p1 and it goes out with a momentum p2. So because let us imagine that you have a wave function with a momentum b, because you can have wave functions with the particular momenta. Okay, you have taken a plane wave with a momentum p. You remember your solutions of the Klein-Gordon field, right? Essentially the solutions of the Klein-Gordon field are nothing but e power I kx, essentially with kx is nothing but k mu x mu nu. Okay, but for a given k, imagine that it satisfies the Klein-Gordon equation, and so this is with a given k, with a given p1 it comes out and it goes out with a p2. Why? Because there is a p sitting here at the interaction, IP essentially, IP I del mu is nothing but a p. So this means, so it is interacting, the current of J mu is acting like a source to the photon, because the photon is the mediator. So what I treat as a photon as a free particle, I still multiply it, but it won't be the free particle solution. It won't be the free particle solution for this vertex, essentially it would be the propagator I have to consider. Depending on the process, there are other, suppose if you are taking pion photon interaction, if you are taking pion scattering of an, or a photon scattering of a pion, in that case another pion will be the interaction with the virtual particle essentially, which is the propagator. So let us just, whatever is a mediator is always a propagator, whatever is a mediator is always a propagator. Now let me not say what is a mediator or not, it is independent, because at this particular point it does not matter what is a mediator, the vertex is just independent of what particle is a mediator. It only tells you that if a pion comes with a momentum p1 and goes out with the momentum p2 and interacts with a photon, that is what it shows you, it has a strength I p2 minus p1. It has a strength of this particular thing, but there is an electric charge also in front of it, so you put it down. Where did I get p1 and p2? There is an opposite sign between, one is an incoming momenta, another is an outgoing momenta. Del mu is a momenta, because the momentum instead of gamma mu in a particular, in the photonic, in the Dirac case you have gamma mu, instead of a gamma mu you have a p mu. So this is a momentum dependent vertex, so it depends upon the particle coming in with what momenta. So it comes with particle momenta p, say p1, and if it goes out with a momenta p2, so there is a difference in the sign. Let me take this sign difference to be p2 minus p1 of mu, essentially of p mu, or if you want to write it p1 mu minus p2 mu. So this is how the interaction is written with the electromagnetic. So this is the leading order interaction, this is the leading order vertex you have. So this is called the leading order vertex. Now you also have the wave function of the incoming pion. Okay, the incoming pion will come with a +1 essentially. Okay, and then there is also a wave function of the outgoing pion, so from the vertex. So everything is defined from the vertex. So everything is defined from the vertex. So outgoing vertex, so from the vertex if something is going out it also gets a -1 essentially. Okay. So this sets your thing for pion scattering essentially, say pi plus pi minus. Now what happens if we have an antiparticle? Antiparticle is again using the Feynman-Stuckelberg interpretation, you should have an antiparticle to be okay, an antiparticle is reverse direction but incoming into the momentum direction is this, but the charge direction is opposite. So this is the momentum direction, say for example this is the momentum direction, but it is coming into the vertex but with an opposite sign of the charge, with an opposite sign of the charge. This is an antiparticle. So this is a particle, this is an particle outgoing. Is there a difference in the wave function for the outgoing meaning for a antiparticle wave function? No, it is still e power I k x with a it is a momentum direction of the if it is incoming, okay, it is only e power I k x essentially, it is just that with a negative energy, the wave function is the same essentially. Okay. So for an outgoing antiparticle, the wave function is also the antiparticle outgoing. Okay. So we define these set of rules for a simple process because we are treating the particle wave functions as free particle wave functions. You are not solving, now this will lead to problems, I will tell you later on why it lead to problems. Okay. So in the Lagrangian I am completely neglecting the interaction part, solving this particular part, okay, and treating these wave functions like in what we do in perturbation theory, and then just multiplying these wave functions here and then using Green's functions methods to calculate these properties and the summary. Okay, and then when you are doing this Green's functions methods, what I am doing is I am deriving rules for this. I am, instead of solving it explicitly, I can derive these rules that if I consider the particle incoming wave function as this and a particle outgoing wave function as this, so as okay, say for example in the case of Dirac the incoming particle wave function would be u functions and the outgoing particle wave functions would be u bar functions. Similarly the antiparticle wave incoming wave functions would be v bar and antiparticle outgoing would be v wave functions. The wave functions are different for and in Dirac case, whereas in the case of the Klein-Gordon field they are all simply the plane waves essentially, they are simply the plane waves, so there is no real spinorial component or something essentially, they do not have anything essentially except that the momentum the energy is of they have negative energy states. Now the wave functions are just plane waves. So with this we are now, okay, I will tell you how you get these rules can be read out when you are trying to solve this thing perturbatively using step by step using Green's function methods exactly like the way I have shown you by for the simple case for one general case I tried to show you that you can always solve the wave function in the presence of interaction at a one particular point, do the time dependent perturbation theory and derive these things, and from this you can read out these rules essentially, do these things you can read out these rules. Now you completely now what you do all your scattering with this bunch of rules, you completely forget about your Green's functions and perturbation theory and everything. There is also one more point which we had to do. Between the vertices there is always a propagator. The propagator for the photon field is eta mu nu by q square. The propagator, the Klein-Gordon propagator which we have seen between the two vertices, which is a bunch of virtual particles, okay, is what we have seen is 1 by k square minus m square essentially. So these are the first bunch of Feynman rules which you have seen, and this you are seeing directly from the Green's functions methods essentially. You can directly see them from the formalism is a bit more laborious essentially, it is a bit more laborious for the thing. I will do it for the Dirac case a little bit just to get your picture, but the formula is exactly the same as this, and from this you can actually derive the Feynman-Stackelberg bunch of equations, and you can forget about the Green's functions methods and take this and calculate your process. Okay, let me stop here and I will continue in the next lecture. Okay, let me stop here and I will continue the next lecture. Thank you very much.